All right, let's talk about centripetal motion. Now, centripetal motion is just a fancy way of saying something is going in a circle, right? So some force must be causing it to go in a circle. If you think back to Newton's first law, an object in motion will remain in motion in a straight line at a constant velocity, and an object at rest will remain at rest, unless acted upon by an outside force. So for something to go in a circle, centripetal motion, there must be an outside force being applied to it. Now, a couple of equations here for you. Centripetal acceleration is the velocity of the object squared divided by the radius. Whenever you plug that in to F equals ma, right, F, sum of the forces equals ma, here, let's get a sum of sign. So this A goes in there. I come out with this equation. Sum of all the centripetal forces equals M times my A, V squared over R. So MV squared over R is my sum of the centripetal forces, aka sum of the centripetal forces is going to be all the forces that point into the circle, all the forces that are trying to make the object turn, minus all the forces that are trying to that are pointing outwards or trying to prevent the object from turning. Note on this, and we'll go over this a little bit more heavily. Forces that are not pointing directly into the circle or out of the circle do not apply here to centripetal force. If it's pointing tangential, and that's a word that's coming, right? If it's pointing tangential to the circle, they do not matter. That would actually go in the other axis. Generally, if you're choosing one location, you're going to choose either the X or Y axis to be where you're setting up your centripetal force equation. Now, two other things that I need to talk about, period and frequency here. Period is the time that it takes to go around one time around the circle, or one revolution, all right? How long does it take you to go around one revolution? So time, period, that means the unit here is going to just be seconds, right? So period, seconds. Frequency is the number of revolutions per second. So in 1 second, I was able to do 10 revolutions. That's the frequency, how often you're able to do something per unit of time. The unit for frequency is 1 over seconds, also known as hertz. Okay, also known as hertz. Now look at the units here. Period is seconds. Frequency is number, right? Just a number which doesn't have a unit. That's why it's just a 1 up at the top. Number of revolutions per second. So you can right there see that period equals 1 over the frequency. And I need to erase my capital P there because that's not a good physics term there. We actually use capital T for period lots of times. Please don't get that confused with tension, though. Be careful with that. If you're putting it into a sum of the forces equation, it's probably going to be tension. Period would be something that you would hold out probably there, or you'd want to choose a different variable. Likewise, you could just flip this equation around, right? Frequency, kind of a script F here. Let's get that to script F. Frequency equals 1 over the period. So if you're ever given frequency and you need to get to period, just 1 divided by it will get you where you need to go. And lots of times you'll be given the frequency and you're going to need the period. I'll talk about that here in a second. Now, centripetal force. The net centripetal force always points directly into the circle. So over here on this picture, centripetal force points directly into the circle along the radius of our perfect circle. Now, if this is an oval shape, things are different. The forces are constantly changing, that sort of stuff. If the forces are constant, though, then we're going to go in a nice perfect circle, and that's what we're going to assume for now in our class. Okay, so all the forces point directly in. On the other hand, the velocity of an object points what's called tangential to the circle. In other words, it's pointing, if you will, straight. Newton's first law, an object in motion wants to remain in motion at a constant velocity in a straight line. But there's some force that causes it to turn, a force pointing in towards a radius. So this force is actually changing direction as the object goes around the circle, right? But it's always pointing in towards the center. So this force, if you will, pulls my mass inwards a little bit, aka around the circle. And whenever we're over here, force again is pulling in. So it's going to continue to pull us around the circle. So here, my centripetal force pulling in, where my velocity is going to still be pointing tangential. On the other side, once we make it all the way over here, centripetal force always pulling into the circle, and because this is somewhat 3D looking, that's why it looks like an oval. Velocity pointing tangential, and just continuing around to the other side, forces, all your centripetal force goes in, and your velocity is tangential. Another way to think of tangential, besides straight, there's two definitions for this. One is going to be a tangential line is a line that only touches a curve at one point. So a line that would intersect the curve twice, and I'll erase this here, would be something like that, right? I mean, it intersects at 2 points, here and here. But a line that only intersects at 1 point, for example, my velocity line over here, it is only touching at 1 point. In fact, if you continue to draw, let's use this velocity up here, if you continue to draw your velocity line down, notice it's only touching at 1 point. That's the definition of a tangential line. Another way to describe the tangential line is that it is always perpendicular to the radius, or perpendicular to the radius of curvature or the radius of the circle. This would be a good time to mention this. Any curve is actually just a piece of a circle. Anytime you have a curve, it's actually a piece of a circle. Take this picture over here. I have a car going around a turn, right? So if the turn is only like this, right, only that part of it, that's not a full circle. But mathematically, we can treat it as if it is. Because if we just continued that all the way around, right, we'd end up in a full circle. So every single curve you ever have has a radius of curvature. That's the exact same thing as the radius, as if that entire curve went fully around into a circle. If the curve just kept going and didn't change at any point in time, right, radius of curvature. So curves, treat them just like circles. Now, what if all of a sudden you stopped applying the centripetal force going inwards towards the circle? What path would that object follow? Ignoring the effects of gravity, there might be some inclination, let me use this picture over here, there might be some inclination that if this object, this ball, for example, is going around, attached by string, going around a circle like this, whenever the string is cut, aka there's nothing pulling it around in the circle, the centripetal force no longer exists, this ball would follow an arcing motion kind of like that, still continuing around, but not in the same tight circle. Well, that's not true, right? Newton's first law, object in motion wants to remain in motion in a straight line. So this object, this ball, would go off tangential to the circle at a constant velocity. So tangential from wherever that string was cut. No more curves. If there is no centripetal force, it does not curve. It's going to go straight, if you will. Now, centripetal force isn't just some magical force, and it's a force that's made up of other forces, right? Things provide a centripetal force. So a ball on a string, the centripetal force is provided by the tension of the string. So you can actually say the tension of the string, which is your centripetal force, tension of the string equals mv squared over r, aka tension is what got substituted in for some of the centripetal forces. A car going around a turn. Think about hitting ice in a car. Can you turn? Well, the answer is no, right? You require friction to turn. The force that would be your centripetal force over here, allowing a car to turn, is actually the force of friction. Okay, so centripetal force is a force made up of other forces. You'll see that in some of the problems that we're going to do. Now let me talk about another idea that that is a misconception. It's the centrifugal force. Think about being in a car. Whenever the driver, or if you're the driver, it turns left, it feels like you are thrown to the right. Okay, it feels like you are pushed the opposite way the car is turned. That's this idea of centrifugal force, a force that pushes directly out from the circle. That's actually not true. See, whenever you are in the car, you're in an accelerating reference frame, which means while Newton's three laws hold in our world, you don't actually see them being held. They break down from your perspective at that time. What's actually occurring is there isn't some imaginary force, centrifugal force, whenever the car turns left that's pushing you to the right. Instead, you're trying to follow Newton's first law. An object in motion wants to remain in motion in a straight line. Your body is trying to go straight, and the car is actually turning out from underneath you. So you're still going straight, and the car is turning out from underneath you, meaning that if you will, if there wasn't friction between your pants and the seat of the car, right, the door of the car would actually turn and then would have to hit you in the arm and push you around the circle because you would go straight otherwise. The car ends up forcing you to turn. So it's that idea, Newton's first law. That's what you would be trying to follow, but the car turns out from underneath you. So in your perspective, you get this incorrect centrifugal force if you're the one in the car. Just know it doesn't exist there. So once again, centripetal force always points into the circle, in towards the center of the circle, and your velocity is always tangential to the circle when dealing with centripetal force. Centripetal force is a force made up of other forces. All right, let me work a straightforward, kind of a simple problem for you to show you how a period might come into these problems. I have a 12-kilogram bucket of water swung around horizontally on the rope. In other words, in the x-axis, not the y-axis. That way we don't have to deal with gravity here. The rope is 0.50 meters, and the bucket makes one revolution every 0.890, 3 sig figs there, seconds. Since they told us how much time it takes for it to go around once, that's the period. Right? What tension must the rope be rated at not to break? In other words, I'm swinging this thing around. If you think about it, whenever you're swinging something, you can feel the rope get tighter. You can feel it that it's harder to hold. So at what point in time, at what tension would it actually cause it to snap? How strong of a rope do I need for this specific situation? So I've got some of my centripetal forces equals the mass of the thing I'm swinging around, specifically my 12-kilogram bucket. The mass refers to what's swinging. Velocity squared divided by my radius. Now I know my mass, it's 0.50. I know my radius, it's the length of the string, right? 0.50 meters, because the rope is what's actually making the circle there. I don't know my velocity, though. I'm told something about my period. And I'm looking for the centripetal force, because the force that makes it up is tension. Tension is my centripetal force. So I'm going to put in a T there for tension, replacing my sum of the centripetal forces. Now, I know mass, I know radius, I don't know velocity, and I need to know velocity to actually figure that out. You can get velocity, though, from this idea of constant velocity. Remember, velocity is displacement over time. And an object going in a circle is going to go around one time around the circle. The distance traveled is the circumference, 2 pi r. Lots of people get the area of a circle, pi r squared, confused there. Circumference of the circle is how far it travels, 2 pi r, divided by time, right? So velocity here of this bucket is going to be 2 pi times my radius, 0.50, divided by the time it takes to go around once, which is the period, 0.890, which gives me a velocity of, whenever you shove that in a calculator, of about 3.5298 meters per second. And that'll allow me to substitute in here and actually solve this problem. So whenever I substitute in my 12-kilogram bucket, the thing that's actually swinging is the mass there, right? The velocity that I was able to calculate using circumference divided by the period, right? Substituting that in, radius of 0.5, it's string length. I come out with this rope better be rated to withstand 299 newtons. Now I only have 2 sig figs, right? This has 3, but we go with the limiting one, 2 sig figs. So that's 300 newtons, or 3.0 times 10 to the second newtons. Now, unit, of course, here is newtons, that centripetal force, right? Tension, it's a force, right? And this trick you see over here, where you didn't know the velocity, you knew the period and the radius, right? To where you use the period and the radius, circumference divided by the period. There, the period's the time it takes to go around. That is a common trick that's going to get used, so get used to that. Sometimes you won't be given the period. You'll be given the frequency. Instead, you'll have to do 1 divided by the frequency to get the period, which then will allow you to use this trick of constant velocity and substituting into your centripetal force equation.